All right, everybody. I think we will go ahead and get started for this afternoon. So, welcome to the session on recommender systems. So my name is Dr. Kevin Moran. I'm from George Mason University, and I will be the session chair for this session today. So we have a mix of the technical track, journal first, and some tool demo papers in today's session that will be looking at different types of recommender systems for software engineering. So one logistical note, we have two mics up at the front, so after each presentation has concluded, please feel free to come up and ask your questions into the mic so that people online can hear the questions and so that we can all hear the questions in the audience. And with that, I would like to go ahead and get started with our first talk. So first up, we have Nathan, who's going to tell us a little bit about developer preferences for using autonomous bots in their development workflows. So Nathan, please come up.
Feel free to clap. Thank you, Kevin. Hi, everyone. Very good to be here. So my name is Nathan. I'm a fourth-year PhD student at Eindhoven University of Technology. And I'll be on the job market next year. And what I want to do here today is I want to talk about our ICSE technical track paper. This is joint work with a lot of great people, Alexander and Andrzej, who are in the audience here today. Yeah, let's continue with the talk. So you might be wondering why, for a presentation about developer bots, you are looking at two seniors and a robot vacuum. And that is because I think that the keynote we saw yesterday by Sarah Pink nicely relates to the work we've been doing here. Because Sarah has been talking about how to design technological systems for a future. And in there we saw the seniors who were quite skeptical of automation and giving control to automation in their home. And with this work we've been trying to we've been exploring this topic as well, and we saw a more nuanced picture, and I'm going to tell you all about it. So I first want to take it back to our motivation. So what we try to do is we try to look at a very broad and open question. We know that developers, they adopt bots, they like bots help them be more productive, but at the same time, bots also introduce noise into communities, and we know that different developers have quite different expectations of software development bots. So we wanted to understand this, and we wanted to ask the open question, okay, what influences human perceptions of bots in software engineering? Now, to answer this open question, we performed a study. I'm going to tell you all about it, but first I want to talk about the takeaway messages for this work. So the two things we discovered while doing this is that experienced GitHub users tend to prefer autonomous bots. So this is a strong signal that we saw. And secondly, what we also saw is that to help developers adopt bots, to help developers be effective, we need more configurability in bot design. Now, how do we get to these findings? Well, we did two different things. We did a two-phase study, and the first thing that we did was we conducted 12 interviews with open source developers. So these 12 interviews we found through convenience sampling, and we asked them very open questions in semi-structured interviews. And the questions went a little bit like the two questions you can see here. So we asked them, what would you feel if a bot rejects your pull request? What would change your attitude towards bot? What would you expect a bot to do in certain situations? And a lot of these follow-up questions, we continued asking them to try and get this picture of, okay, how do developers or how do open source developers think about bot behavior in their communities? Now, we analyzed these interviews, and there's a lot of great stuff in these interviews. And we have a replication package where you can read each of the anonymized transcripts. So please do so if you're interested, because I'm just going to highlight two themes that we focused on for the rest of the study, but there's more in these interviews. So the two themes that we saw, the two things that developers kept talking about, were that it mattered their attitude towards the bot depended on the persona that the bot exhibited. So did the bot use very informal, very chatty language? Or was the bot very formal, very factual? And the second thing that we saw is that to developers it mattered whether the bot had autonomy within a community. So was it able to take actions independently, or did developers need to explicitly trigger it? So we thought that these two constructs were very interesting, and to further explore them, we continued on with an experimental survey. The choice for this experimental survey to discover or to look at these two topics was based on the fact that ideally we would want to do this in a lab setting where we have a lot of control. But this is not feasible because, of course, it's expensive to bring developers into a lab, and it's expensive to set up these sort of setups. So we had to make a trade-off, and we opted to go for an experimental survey where within this survey we reconstructed parts of the GitHub interface, and we brought in two groups of participants or two groups of respondents, and we asked them to fill out this experimental survey. Now, what I want to focus on for the remainder of the talk is I want to highlight two different things. I first want to talk about our sampling using Prolific, and I want to talk about the experimental platform that we used. So for those of you that are familiar with sampling through Prolific, one of the known issues that we see is that people pretend to be software engineers on Prolific without actually being software engineers. So you can equate this to kids trying to sneak into a cinema and trying to pretend like they're software engineers. So following best practices in our field, we set up a pre-survey evaluation, a pre-screening, where we filtered out users that were not actually software engineers. So we did this using questions you can see here on the slide. Very simple, basic programming questions that we expected every developer to be able to answer effectively. Now, like other studies, we see that only 10% of the users that we paid to take the survey were actually able to answer a series of 6 of these questions. So that's quite problematic. What we expect to be even more problematic is the fact that we ran this survey before ChatGPT, before large language models. Yesterday, I pasted this question into the interface of ChatGPT, and it was able to answer it perfectly. So I think one important thing that we all need to focus on is we need to think about these pre-survey screenings, and we need to think about effective ways we can do this, because these sort of like simple questions won't work anymore, because these models are able to answer them. The second thing I want to briefly show you is I want to show you the interface that we used. It might be a bit difficult to see here, but we reconstructed parts of the GitHub interface. And here you see that a bot is opening a discussion. Now, in the same screen, we showed our participants 2 interaction models side by side. In this case, you're looking at the autonomy. So either the bot opens the discussion or a user triggers the bot. And we asked developers, all right, which side do you prefer? Which interaction model do you prefer? To ensure that developers picked a site purposefully and they weren't just distracted by either the color of the avatars or they were distracted by things we didn't want them to focus on, we primed them. Additionally, we also asked them to provide a reason for their choice, and we manually validated this to see that developers were actually picking a site because of the reason. Now, of course, we had several of these scenarios, and we divided them into 4 different vignettes for different scenarios. So either developer could pick between proactive and reactive bots, and the language that the bot used was fixed, or vice versa. Now, I want to show you one of the results that we obtained. And if you look at the bar plot here, the differences might be difficult to see, but if you look at the choice for reactive and proactive, and you look at experienced developers, the blue bar, you see that more experienced developers tend to prefer proactive bots. Meanwhile, if you're an inexperienced developer, there appears to be a strong preference towards reactive bots. Now, we have 3 more of these bar plots, so I'm not going to show them in the interest of time, but what we did do as a follow-up study is we continued looking at this because we were interested to see, okay, what could explain these differences? Does this really have to do with the experience? Does this have to do with something else? So we did some Bayesian statistics. We tried to fit different models, and we tried to see, okay, how well do these models explain the underlying data? What you see here is you see the output of, or you see the 2 models that best explained the situation, or that best explained the data. So when it comes to the choice for autonomy, the GitHub experience appears to be very decisive. So the more experienced you are, the more you tend to prefer autonomous bots. Meanwhile, when it comes to the choice for persona, this was much more nuanced because this appeared to depend on not only the GitHub experience, but also the programming experience of our respondents and their preference for autonomy. So this seemed to indicate to us that maybe there's something else that determines whether a developer likes the way a bot uses language and whether it's very informal or whether it's very chatty. Now, Yeah, so this was the modeling that we did, and these were the two models that best explain what was going on with the data. Now, I want to close with our takeaway messages. And what I first really want to emphasize is this point of this prolific pre-screening, because we have to be very careful with this as a community, I think. And then secondly, I want to re-emphasize what we see here, and that is, of course, that autonomy appears to really be something that experienced developers prefer more. Meanwhile, we should be more mindful when we're designing these bots, and we should be thinking about, okay, what sort of interaction models do individual developers want to use when they're interacting with these GitHub bots? And maybe this should be something that an individual can configure, and that's not something that's fixed for a single bot. And that was the study.
Thank you very much, Nathan. So if we have any questions from the audience, please feel free to come up here and to ask your questions into the microphone so that we can all hear. And don't be shy, please come up. But while we are, question? Yay, excellent. Please go ahead.
Hi, thank you so much for the nice presentation and interesting study, actually. I have one quick question. So I like the last message you presented about configuring how to interact. So as a chatbot developers, right? So what kind of advices you suggest or do you recommend when developing chatbots? Because, you know, for example, when we deploy the chatbot, publish the chatbot, there are many users, right, with different ways how to deal with the chatbots, and we are somehow limited into the terms of the configuration that we can make it configurable by the users. So I would like to hear your opinion on this.
Yeah, so thank you very much for the question. I think that's a very good question, and I think that's something that we should definitely try to explore, because for these scenarios, we really picked the two polar opposites. So we had very brief factual messages, and we had very chatty, informal, hi, nice to see you, thank you for contributing to this community. And when we looked at the open messages that respondents indicated for their choice, for which language they preferred, they really indicated that sometimes people really like this sort of like informal way of being approached by a bot, and others really like the fact that it was just short to the point because they knew it wasn't a human typing this, they knew it was some sort of automation. So I think when it comes to this, that we should experiment with this a little bit more, but a good starting point would be this sort of like information density, either offering very short, very factual messages, or just a lot of information surrounding it that's just informal, normal, like human courtesy.
We know open source communities, they're managing lots of different types of contributors, right? They have the veteran contributors who have been around for many years, that know the project really well, and hopefully there are newer contributors, or people that are kind of onboarding onto the project. Given these different populations of users, if there was, let's say you were going to be advising an open source community in terms of whether or not they should apply a certain bot in certain circumstances, could you give any sort of general recommendations, maybe either for the veteran users or for the people who may be onboarding on, or their specific like types of bots, like ones that are just going to greet them or like suggest first issues or other things like that? I'm curious.
Yeah, so thank you for the question. I think the most important recommendation would be towards the maintainers that choose to adopt a bot within a community to be very mindful of the way the bot responds to newcomers that might not be familiar with these interaction models. So we see that newcomers have a lot of barriers in open source projects, and I think that sometimes when these bots are very factual and they just close a pull request because there's some reason and there's not a lot of explanation on what's going on, that this just scares people away that are not familiar with this. So I think that should be the most important part, to be very mindful of this.
Not sure if co-authors are allowed to ask questions, but
That depends on how difficult the question is.
yeah, it's difficult, I think. So we were lucky because we did all the questionnaire work before ChatGPT was released, right? Is prolific dead now? I mean, this whole pre-check idea doesn't make sense anymore. Was it the last time we used it?
I know that we looked at the time it took for someone to answer these questions. That if you took a lot of time, you were probably researching these questions, because that's always a risk that you have. Now with ChatGPT, because you can instantly get these questions answered, I'm not sure if we can still use it or if there's maybe some other pre-screening that we can effectively use, or maybe there's some other thing where Prolific needs to check the credentials of people that apply to their platform before people can actually answer questionnaires, because that could also be one of the solutions, of course.
I think that's all the time we have for questions, so let's give another round of applause for Nathan. Okay, and up next we have our next technical track paper. So this is going to be exploring how we can improve dependency management, which is a headache for many developers. So our next speaker is going to talk about how we can wrangle this problem using a technique based on Max-SMT. So please, whenever you're ready.
Hi everyone, my name is Donald Pinckney. I'm a PhD student at Northeastern University. And today I'll be talking about the work that I've been doing with my collaborators on flexible and optimal dependency management via Max-SMT. So let's first take a brief look at what dependency management typically entails. So for example, if I work in the JavaScript NPM ecosystem, I have to specify my dependencies in a package.json file, as shown on the left. I write down what packages I depend on, and specifically which allowed versions of those packages are acceptable to me. Then I would typically run npm install at the command line, and then that will install a bunch of packages, specifically which versions of those packages. Okay, but unfortunately this is not the end of the story. This solution may be unacceptable to me for a variety of reasons. First, I may actually end up with a bunch of duplicate dependencies, in which I have multiple different versions of the same package installed. This can be bad for two reasons. First, it means that code size is a lot larger, which may be certainly concerning for web apps. And secondly, this may actually be a logical error if that package, for example, mutates global state and so on. Secondly, I may end up with security vulnerabilities in this solution, which certainly is not a positive thing. And third, I may actually end up with older versions of packages than I was expecting. So in the top right here, I got glob version 7. I think there are new versions available, and yet I didn't get it. Why? Well, because of NPM's complex and rather strange solving algorithm. Way deep down in the tree, there was something else that then forced me to get this older version. Right, so depending on which of these problems actually occurred, I then have to take manual steps to address the problem. So I may have to modify my constraints manually so that I am force npm to definitely give me the newer version of my dependencies, right? To address the security vulnerability, I can try using the npm audit fits tool at command line. However, this often actually fails to really fix the problem. And failing that, then I would have to again go and fix my constraints manually by explicitly disallowing the newest version of the vulnerable version, right? So that I purposely get an older version that's not vulnerable, right? And to fix the duplication problem, I could try using some bundler tools such as Webpack, which deal with the deduplication sort of at the source level. But if we take a step back, what are we forcing developers to do here? Right? They have a solution that they're not happy with the dependency solving. And to address it, they have to either use a bunch of ad hoc tools to modify their dependency solution after the fact, or they have to hard code their preferences into their constraints in order to get the solutions that they want. And this is really not that composable, because then clients that depend on this package, well, then they're forced into making that same preference as well. So in this talk, I want to present a different vision. So the last talk talked about customizability. It turns out I am too. And in our view, what's key here is that different developers have different needs for dependency management. Some developers actually really care about security, right? But other developers, just depending on the deployment environment and so on, maybe code size matters more. And we believe that dependency solvers should allow for this customization. And further, if properly designed, we believe that these dependency solvers that are flexible could replace many of these ad hoc tools and sort of manual labor that developers currently have to go through. So to understand this design space a little bit more deeply, let's first take a step back and shift our mindset. So instead of thinking about dependency solving as simply understanding what NPM's sort of specific and rather weird algorithm does, let's instead think abstractly, what is the allowed space of solutions? We have multiple, potentially a lot of different solutions in the space that would satisfy the constraints on the left. And then when we have this space, we can then look inside the space and find that there are indeed subspaces in here, which may meet our requirements depending on our different preferences. So some of these solutions are the solutions that have lots of newer versions of packages. A different space up in the top right is the space of solutions that are smaller on disk, and so on. So our second insight is that we may then use additional constraints and or optimization objectives to then guide solvers to find solutions in these subspaces that we would prefer. So to get there, we are presenting two technical pieces. So first we have PackSolve, which is our framework for configuring dependency solver semantics. And then built on top of that, we have Max-NPM, which is a drop-in replacement for NPM. And it allows for customization of solving configuration. And it uses PackSolve as its backend. So let's take first a brief look by example through PackSolve to see how it works internally. So internally, the first step with PackSolve is to give it, what is the syntax of versions and what is the syntax of version constraints? So in this example, I'll say versions are simply a 3-tuple of natural numbers, and constraints, well, they are given by this abstract algebraic data type in which we have equality, less than or equal to, greater than or equal to, and conjunction, right? But what does all of that mean? Well, next we have to tell PackSolve what are the semantics of these constraints. In other words, we have to be able to take a constraint, a version, and then compute if the version matches the constraint. And we can do that sort of via simple pattern matching plus structural recursion. So at that point, we've specified what I call the base semantics to PackSolve. And at this point, PackSolve will function as an executable dependency solver. However, it will be rather undefined which solution it will return. So to fix that, we can now put in our customization options, right? And specifically, we can use optimization objectives to guide PackSolve to choose the best possible solution. So if our choice is we want to minimize the size of the solution, then this would be the optimization objective we would choose, in which we minimize the total size of the solution graph. Okay. So that's the internals of PackSolve. Now we build a actual command line tool, Max-NPM, which is essentially a wrapper around it specific to NPM. So it involves formalizing the entire constraint language and semantics of NPM, right? And then when this tool needs to solve dependencies, it ships the query off to PackSolve to actually perform the solve. Right, and then what this tool allows is it provides command line flag options so that developers can then choose how to customize it at runtime. So you can say here at the bottom, you can say, oh, I want to minimize at the higher priority, the choosing newer versions of packages, and the size of the graph. Great. So this all seems hopefully cool, but does it actually work in practice on real packages? So specifically, we break this down into two questions. First, does Max-NPM actually find better solutions than NPM? And we'll look at the case study of minimizing the security vulnerabilities that are installed. Secondly, does Max-NPM actually integrate well with existing projects? So first, let's look at this security vulnerability case study. So here we configure Max-NPM so that it minimizes the total aggregate CVSS score of all installed packages in the solution. And when we do this, we find that 33% of the packages we test, on those 33%, we can actually reduce the security vulnerabilities that are installed. So an example is with the Babel compiler, when we install packages using Max-NPM compared to NPM plus NPM audit fits, we can actually reduce the aggregate CVSS score from almost 60, which is around SITs, like severe level bugs, down to 0. And then an additional question is, does do Max-NPM solutions actually pass existing test suites, right? This is really asking the question, can an existing developer of a package start using Max-NPM, like sort of for free? If the solutions that Max-NPM gives would pass existing test suites, then that means developers can really easily start using it without too much headache. And fortunately, we find that only 6% of packages we test actually change their test behavior under Max-NPM versus NPM. So that concludes my talk. Thank you. To summarize, we first took a more general look at dependency management and sort of all the headaches that it may entail. We argue that a sort of more flexible model for dealing with this space is to implement customizable dependency solvers, and we argue that doing this via optimization objectives with Max-SMT is a positive and fruitful way to go about that. Thank you.
Thank you very much, Donald. Questions from the audience? If you were going to place this in front of developers and have them actually use it, is the constraint solving procedure, is it going to be fast enough for people to, to work in a reasonable amount of time where they're not waiting too long?
So 2 things. So first, yes, how much slower? So, there is a performance cost. It is not free. So what we really see, and this I think mirrors other things in the stat solving world, on sort of the vast majority, it's maybe about the same or a little bit slower. So we see that on sort of non-outliers, it adds like, at the mean, like 3 seconds of solving time, which is fine. But then there is like a tail, certainly, which could add like a lot of time and sometimes like timeout at like, 10 minutes or something, right? But fortunately, that's fairly rare. And, we do see that it does scale up to like cases of like, over 100, 200, 300 sort of solutions. But like, there are some crazy ones that like have like solution sizes of like 1,000 packages, and we do break down at some point. So that's sort of something you need to improve on. Thank you.
Yeah, thank you very much. And I want to say too, as someone who has dealt with NPM's, let's say, mysterious way of handling dependencies sometimes, this is interesting work.
Thank you.
I had a question. If you plan to work with Max-NPM with tools such as GitHub Actions, where you can automate the runs to acknowledge like vulnerabilities and the other types of customizations.
Yeah, if I'm understanding your question correctly, I guess you're sort of asking about like what's the future of like using this in like CI and sort of automation like that. Yeah, it's worth thinking about. So I think it's a good question for the future. Definitely the sort of setup that we have right now is that it does sort of integrate with vanilla NPM in the sense that, you can do one of these optimal solves, which as the chair mentioned, may take some time, right? But then you can sort of save that, and then CI can then like read that solution and then install that like very quickly using standard NPM. But going forward, I think there's definitely opportunities for more like automation to sort of do the solving like sort of continually on CI in the background or something like that. I don't know.
Thank you so much.
Yep, thank you.
Have you engaged with the NPM community at all and kind of showed them what you've done here? I'd be curious to see if they have thoughts on it.
That is definitely important to do next. Yes, that's a pretty high priority. I would also briefly mention, if anyone wants to use the tool, it is available to install via NPM, so you can install Max-NPM via NPM, which is pretty cool.
Awesome. Thank you very much, Donald. Let's give Donald another round of applause. All right, so our next talk will be a virtual talk from the Software Engineering in Practice track on a topic that has received, I think, quite a bit of attention recently. So this is going to be looking at, how we can design AI-assisted programming tools to be more useful for developers and really improving the user experience of these tools. So I will go ahead and turn it over to the virtual presenter. There we go. You are on the screen, and we're looking forward to hearing from you.
Hello, thank you very much. I'm Priyan Vethalingam. I'm a graduate student at Harvard University, and this work was done along with many teams from Microsoft Developer Division towards improving IntelliCode's user experience to show AI-based code generation systems. And as we all know, the AI-driven code recommendation systems has had a huge uptick, and a lot of different tools are coming out. Copilot, Tab9 Pro are some of the many tools that are coming out uh, for AI-driven code recommendation systems. And in fact, even in Visual Studio, we have IntelliCode, which has tens of already implemented AI-based code recommendation systems for, generating, modifying code, even up to debugging and stuff. And a problem which we found was that there was some issues with discovering these AI-based suggestions, because the newer features of these code recommendation tools are being added to the existing traditional interfaces like light bulbs or drop-down menus to show these code suggestions. This is true for Visual Studio or even for other IDEs like IntelliJ, where existing traditional interfaces are being used, but users are having issues discovering these recommendation systems, mainly for a few reasons. The light bulb or menu interfaces are not proactive, and it requires a manual initiation. So the user has to know that such a feature exists, and they have to know how to initiate this feature, and also have to know when exactly to initiate this feature to get the best output. And if under any of these circumstances they fail, they just don't use the system in the most optimal way. So to fix this, there are tools like Copilot, which actually use inline interfaces that are a lot more proactive. So you don't need to go and manually initiate it, as in when you're typing the code, and whenever it has a suggestion, it just shows you inline, and accepting or rejecting the recommendation is as easy as pressing a key, and you don't have to figure out when to do this. So you don't have to remember to initiate it. You don't need to keep track of what all new features are being added. It's very much proactive, with one downside that this can be distracting if taken to another extreme. So naturally, we asked the question, like, how can we leverage inline interfaces to show AI-assisted code changes for not just very simple addition of code, but for much more complicated use cases? So we split these into 3 stages. One is additive code change, which is similar to Copilot, where we suggest code that is being added to existing file. And the other one is single line code modifications, which are modifying a statement or an expression, but restricted to a single line. And multi-line code modifications, which can span from 2 to many lines during the recommendation. And we started designing for each of these stages, each of these types of code change. And our exploration method was very comprehensive. So we generally start with multiple parallel designs for each of these elements, generally from 8 to 10 design prototypes. We then filter this through voting. And then based on the voted filtered designs, we do an extensive user testing where we put these prototypes in front of actual customers who use Visual Studio, and then get feedback from them. And once we get the best design, we take that design and user feedback and iterate all over again. So we have tested this over 61 participants in person, and we have actually explored over 50 designs in this exploration. So a brief overview is like we started with additive code change. We did a single iteration, and as we went for more and more complex use cases, we did more iterations with more number of participants. We also did a few field deployments, which I'll talk about later. So we started with a very simple use case for additive code recommendations. This type of muted gray text code recommendation is already being used by Copilot and IntelliCode whole line completion, but there wasn't any usability studies done to understand, do users actually prefer this? How can we make it better? If it's better, why do users prefer this? So we showed this to a bunch of participants. And when we did the study, we actually realized only one of all the participants we tested knew that this feature existed inside the lightbulb already for a while. And users did not know until we showed them a gray text user interface. And we also found out that these GreatX user interfaces are actually a lot more discoverable since they are very proactive. And the muted GreatX, clearly indicated what was suggestion and also like added very little visual clutter to the interface. So we moved on to designing for single line code changes. And I'm showing some of the many designs we explored. We explored some designs using diff view based on version control systems, which we are very familiar with, and GreatX, which Copilot-based systems already use, which seems to be very popular. We took a bunch of these designs and gave it to the users to check which one suited the best. And surprisingly, what we found was people did not really prefer GreatX designs for code change suggestions because the diff view actually gave a better juxtaposition of what the old code and the new code and the change being proposed is. Even though the code which the participants are working on are probably written by them, they would still prefer to see the code that is being affected. And the diff view was preferred by the participants because they already have experience with diff views. They understand immediately what is being removed, what is being added, and follows a very familiar visual motif. So all of the participants preferred diff views. And also, GreatX or modifying the code automatically while showing the recommendation, participants generally dislike because they felt like we are mucking around their code and mangling their code. But whereas diff view, while showing it to the side, felt a lot more subtle. Once we figured out what is the best way to show single-line code suggestions, we extended it for multi-line code suggestions to check if similar kind of diff view will work for code suggestions that are longer than a few lines of code, or will pop-up based interfaces work. And so we designed a bunch of interfaces for multi-line code change. While doing this design, we found a special use case for multi-line code change where there is a template-based suggestion where we do not have to always show the whole diff view because the changes are pretty uniform and consistent. So we did a special design for template-based suggestions for testing. And we tested this again with around 33 participants. And the results we found was for code suggestions that are longer than a few lines, participants wanted to see the whole suggestion in their view and did not prefer when it spilled over their screen real estate. They did not prefer to scroll. And somehow adding a scroll element, or if it spills over the screen, it adds a lot more cognitive load to the participant, and they prefer to just reject the suggestion or even turn it off. Participants did not prefer pop-ups because it added a lot more visual clutter and it's hiding code under its view, and anything they feel is visually heavier automatically makes them feel that they have to work a lot more harder to understand the suggestion, and they just generally dismiss it. Participants prefer the template-based suggestions more than the diff view for if whenever possible, because it again showed a lighter UI, and also like it was very familiar based on other places they have used these template views, like renaming a variable and places like that. Since it was very familiar for them, participants prefer to see the template-based designs wherever possible. And automatic preview, which we thought would be very helpful to participants, was actually what turned out to be not at all helpful. Participants did not want any kind of automatic changes, even if it is transient and temporary in their code, because it felt like they are losing control of their code and their tool to an AI tool. So this was those subtle, very important distinction which participants drew. So after all these studies, we actually deployed some of our designs in the field. For additive suggestions, we deployed inline GreatX interface as a part of Visual Studio Global release. And the number of users who used this particular recommendation, which was already present for many years in Visual Studio, tripled. And even though this kind of suggestions was only 25% of all the suggestions recommended by Visual Studio. It contributed to 60% of all the suggestions that were accepted by the users. This was an immediate hit. And for single line code change, we again took the best user interface and then did an A/B test with Visual Studio Preview users. And there was an immediate increase, 1.76 times increase in the number of accepted suggestions, and 29% increase in the number of new users who are using these features, even though this feature existed in Visual Studio for a few years. So based on our user study and our field deployment, we have a few design takeaways for future tools. This first one is glanceable suggestion. For the suggestion to be discoverable, it needs to be glanceable at the right moment. We believe inline code suggestions are glanceable by directly being rendered in the code editor so that the user doesn't have to guess when to initiate the AI tool. For our code recommendations, we believe inline code suggestions were the best option. But for other kinds of code recommendation, inline code suggestions may not be the best, but it needs to be glanceable at the right moment. We should take the user's guess out of the equation. And second thing is juxtapose. Always juxtapose the old code with the new code and be very clear about the scope of the code that is being affected by the suggestion so that the users do not have to guess. As soon as you make the user assume and guess, it actually adds to the cognitive load, and then they find it a lot more effortful to accept the code suggestion, and they just generally start rejecting after a while. And the second thing is simplicity through familiarity. There are a lot of interfaces and interactions which are already present in IDEs, which users are used to. So just using familiar visual artifacts and interfaces actually reduces the visual clutter. Reusing existing interfaces like the way we did diff views and template-based designs actually helps the user to understand the recommended code faster, and which enables them to take action on it faster. And sufficient visibility for validation. Almost all of the users we showed really long code change sessions preferred to not scroll and not take actions to see the whole recommendation. It's always better for the users to see the whole recommendation at one glance for them to validate and take action. And the most important thing is snoozability of suggestion. With more and more AI-based code recommendations being pushed, if every single feature becomes an inline code suggestion, users will get tired of seeing these appear over and over again. So all of the users asked for a way to snooze when they are in the code authoring mode, when they do not want to be disturbed by code recommendations. And it is vital to allow users to pause. If not, they will mostly just turn off the solutions. So these are the 5 design principles which we believe can help future AI-based code recommendation tools to be a lot more usable. And that's my presentation. Thank you.
Okay, so I have a question for you. So I don't think this was a parameter of the user studies that you looked at, but I'm curious, for the different types of changes and suggestions and things like that, did you notice any patterns about the specific context of the code being suggested? So if it was a method signature versus a variable declaration, or a conditional for a loop or something like that, do you think there's anything to be gained by maybe combining static analysis and seeing what the context of code is and how that might change the user experience for some of these different suggestions?
Yeah. I think if you do use static analysis to give a little bit more context of why this code recommendation being suggested, that will be very helpful for the users. But one thing we noticed was, which we didn't mention in the paper, but we did a lot more studies on showing explanations on why this code was being recommended. And mostly users just did not read the recommendations. We did some eye tracking studies and a bunch of studies to see why users are not seeing recommendations, and they just it's right in front of their eyes and they just skip over it. So it's very difficult for us to, it's very difficult for us to show things which the user doesn't want to see, how much our, big and bold we make it. So we need a better way to show these contexts, which like the contextual information from static analysis. It's an open question. I don't have the answer to.
Great, thank you. Looking forward to the next paper then. All right, so let's thank the speaker one more time. So next up, we have a tool demonstration paper that is exploring how we can use deep learning to give us log recommendations. And this is going to be another virtual presentation.
Log recommendation plays a vital role in analyzing runtime issues, including anomaly detection, performance monitoring, and security evaluation. Our existing deep learning-based approach for log recommendation suffers from insufficient feature and low F1. To this end, this paper proposes a prototype called deep log to recommend the log location based on a deep learning model. There are three problems that we will resolve. The first, existing works are prone to leveraging single feature. Few works extract semantic, synthetic, and structure feature from source code. Secondly, in the serial cross project, there is still a lack of guidance to decide which project should be selected to build the training dataset. Thirdly, most log recommendation implied machine learning models. The work based on the deep learning model needs to be further developed. This is our result. We will use log hierarchical tree and similar analysis and plug in to solve these problems. This is our dataset. To generate samples, we select 23 real-world projects that are commonly used in parallel log-related studies. By doing this, we construct a dataset with more than 1,000 samples, and we apply the undersampling technique to mitigate the impact of data imbalance. This is our overview.
As we explore the world of hybrid conferences, there will be hiccups along the way, but at least we get to see what is being presented here. Okay, so it looks like because of these technical difficulties, we're going to go ahead and move on to our next speaker. So this is going to be another tool demo presentation on Shell Fusion, which is an answer generator for shell programming tasks that uses knowledge fusion. So this will be our last online presenter, and hopefully we can switch over. There we go. You are on the screen, and please begin whenever you're ready.
Hello, everyone. It's my honor to present our work at ICSE. In this work, we propose a web-based tool, Shell Fusion, a tool to automatically generate comprehensive answers for shell programming tasks. In Unix and Linux platforms, shell programming is widely used to accomplish multiple tasks such as file manipulation and network management. However, the large number of commands available makes it a big challenge for programmers to find the appropriate commands for a task. More than 50,000 shell commands are documented in the Ubuntu manual pages nowadays. Therefore, we introduce a novel web-based tool, Shell Fusion, which can automatically generate answers for shell programming tasks by integrating multi-source knowledge of shell commands. As we can see in the diagram, the workflow of Shell Fusion consists of two main components, the offline processing part and the online part, and has 5 steps in total. In the first step, we first collect shell-related question posts from the 4 main coding Q&A communities, which are Stack Overflow, Unix and Linux, Superuser, and Ask Ubuntu. Moreover, we parse Ubuntu manual pages TLDR tutorials respectively to obtain knowledge of commands. In the second step, we first build a text corpus by processing the shell-related questions. Afterwards, we build a word IDF vocabulary and a word embedding model based on the corpus. Moreover, we create a document for each shell-related question by collecting the title and text and index them using Elasticsearch for efficiently retrieve similar questions. The online part contains 3 steps. In the first step, given a query describing a shell programming task, we first retrieve top 1,000 most similar questions by using the Elasticsearch engine. Then we filter out the top 50 most similar questions according to their similarity by leveraging the word embedding model and word IDF vocabulary. In the second step, we first obtain a set of candidate commands from the accepted answers of the top 50 similar questions by measuring their similarities with the query. Afterwards, we re-rank the candidates to get the top 5 commands by considering both the number of accepted answers that use the commands and the similarities of questions. In the final step, Shell Fusion used the MP and TLDR knowledge we parsed in the offline processing part to generate comprehensive answer for each of the top 5 commands as shown in the user interface of Shell Fusion. The 4 aspects are MP summary, most similar TLDR task script pair, top 3 similar questions with accepted scripts, and explanation about options. While MP summary and explanation about options synthesize knowledge from MPs, the TLDR task group pair part synthesized knowledge from TLDR. To evaluate Shell Fusion, we conduct an experiment. We compare Shell Fusion with Magnum and state-of-the-art approach for translating natural language tasks to bash commands in the experiment to evaluate its correctness. Furthermore, we conduct a user study to evaluate the usefulness and understandability of the answer generated by Shell Fusion comparing with Magnum div-A answer, a model that uses DL technique to recommend answers, and web searching engine, which is WS. As Table 1 shows, Shell Fusion outperforms Magnum by at least 179.6% in terms of MR at K and NAP at K. And the usefulness and understandability score of Shell Fusion is 3.553 and 3.766 respectively, which are significantly bigger than those of other approaches. Both results imply that the answer generated by Shell Fusion is correct and easy to understand and can help users quickly find their expected commands and scripts for queries. In conclusion, we developed Shell Fusion, a web-based tool for thematically generating comprehensive answers for shell programming tasks by fusing knowledge from multiple sources. The results of the experiment and user study confirms not only the correctness, usefulness, and understandability, but also the superiority and practicality of Shell Fusion compared with the state-of-the-art approaches in generating answers for shell programming tasks. This is my presentation, and thank you very much.
I have maybe one, maybe fairly obvious one, given kind of some of the recent advancements in large language models for programming tasks. So, have you looked at things like ChatGPT, Bard, other things like this that may be able to answer similar types of questions, and thought about maybe advantages that your tool has over some of these models? Maybe it's able to give more specific answers or recommend higher relevancy ones. I'm curious if you've thought about this since you've worked on this. I think probably this work was kind of completed before a lot of these got really popular, but I'm curious if you've explored that.
Yes, ChatGPT is really popular these days, and our team currently is working on improving the Shell Fusion. And one of my thoughts is to use ChatGPT and integrate it into our tools, but it's just a way. And in my experience, when you ask ChatGPT a programming tasks, it seems to always leveraging already exist answers from the internet, and you will contain some of the segmentational thoughts, and the ChatGPT seems to always refuse to change the wrong part. yeah, that's my own experience.
Very interesting. Thank you. Yeah, I look forward to seeing your next paper where you examine the weaknesses and strengths of both tools and see how you can improve upon them. So let's give our speaker another hand. Thank you very much.
Thank you very much.
All right, so next up we have an in-person presentation now for a journal first paper that is looking at revisiting and benchmarking a really popular topic of research in API recommendation systems.
So, hello everyone. This is Yun Peng from the Chinese University of Hong Kong, and today I'm very happy to come to the ICSE conference again and share our work named Revisiting, Benchmarking, and Exploring API Recommendation. How far are we? So, the API or Application Programming Interface, which encapsulates the implementation of specific functions that could be reused in different software, can largely improve the programming efficiency. And nowadays, even the simplest Hello World program involves at least one public API. However, with the development of software, there are a lot of APIs being designed. And even the Java standard library have at least 13,000 APIs, and therefore even the most skilled developers cannot be familiar with all the APIs. To address this problem, there comes the API recommendation, and it recommends the proper API to developers according to the task description. And based on the format of the task description, we classify all current approaches into two categories. The first category is query-based approaches, in which we can give them a natural language query, and then they will reformulate the query via query modification, in which some existing words are modified, or via query expansion, in which some new words are added into the query. And then some retrieval-based and learning-based methods are implemented to find the proper API given the reformulated query. And another kind is code-based approaches. In these approaches, we can give them an incomplete code piece with a recommendation point, and then they will use some pattern-based or learning-based methods to find the proper API that should locate on the recommendation point. And given these two kinds of approaches, we build two different benchmarks for them. First, for query-based approaches, we mine the Stack Overflow posts and collect all posts from 2008 to 2021, and we then implement some rule-based filtering method and combine with some manual check, and finally obtain about 1,000 Java queries and 2,000 Python queries. We also mine the queries from 3 well-known tutorial websites and obtain about 5,000 Java queries and 2,000 Python queries. And the table in this slide shows the statistics of our benchmark for evaluating query-based approaches. And we also implement some widely used query reformulation techniques on the original queries collected in the benchmark to enrich our benchmark. So for the code-based approaches, we collect the code pieces from the repos at GitHub according to the domains classified by the GitHub topics page. And generally, we collect 500 to 1,000 most start and most focused wrappers at GitHub to form our benchmark. And to study the query-based approaches, we select 4 popular query reformulation techniques and 6 existing query-based API recommendation approaches. And first is the effectiveness. We evaluate all 6 query-based API recommendation approaches on our benchmark, and firstly, we compare them class level and method level performance. So for the class level, we require the approach to give the class where the API comes from, while in the method level, we require the approach to give the exact API method. So the class level is much easier than the method level. And from this table, we observe that generally the class level of current approaches is much higher than the performance of the method level. And almost about 60% of method level APIs can be successfully predicted at the class level, but not at the method level. Therefore, accurately recommending the method level APIs still remains a great challenge. And to study the impact of query reformulation techniques, we apply these techniques to the original queries in our benchmark, and we then see the improvement brought by them on current query-based API recommendation approaches. So first, we find that the two figures in these slides shows the improvement brought by query expansion techniques and query modification techniques. First, we find that the query formulation techniques, including both query expansion and query modification, are quite effective in helping current approaches to give the exact correct API. And we also observed that query expansion actually is more stable and effective than the query modification techniques. And to study the code-based API recommendation approaches, we select 4 widely used IDEs and 6 academic approaches. Also, for the effectiveness, let's first look at the performance of academic approaches. From this table, we can see that deep learning models' travel trends show superior performance by achieving a top 10 success rate of 62%. And when comparing the performance of academic approach with the widely used IDEs, we find that first, in Python baselines, travel trends still obtain the best performance. But the IDE PyCharm also obtain a competitive performance. And in Java baselines, surprisingly, the widely used IDE, Intelligent IDE, obtained the best performance, and its performance is much better than the academic approaches. So this suggests that widely used IDEs also obtain competitive performance with the academic approaches. So lastly, we study the cross-domain performance of current code-based approaches. And we find that generally the performance of current code-based approaches drop if they are trained in one domain but used in another domain. But interestingly, we also observe that training on multiple domains helps the current approaches to recommend APIs in different single domains. And the performance is even better than only training on the certain single domain. So the above is a brief introduction of our paper where we talk about the background of API recommendation, the benchmark we built, and some interesting findings for both query-based approaches and code-based approaches. So you can also access the 2 QR code in this slide to get our benchmark and paper for more detailed research questions and findings. Thank you.
So I have a question related to the findings of your query-based approaches. So
okay.
I'm curious if you did any investigation into why you saw that the query expansion techniques were a bit more stable, provided a bit more benefit overall. Do you have any insights into why that's the case?
Yes, I think a possible explanation for the effectiveness of query expansion techniques is that query expansion techniques can add extra knowledge to the query and to supplement the intention of the developers, so that the current approaches can benefit more from the more knowledge in the query to find the proper APIs. So this is why the query expansion techniques are more effective. Yeah.
Yeah, it seems like that extra information really pays off in retrieval.
Yeah, that's true.
All right. Well, thank you very much. Let's give the speaker another round of applause. Okay, so next up, we have another Journal First paper that is exploring semantically enhanced topic recommendation systems for software projects. And I believe we'll have Malaya, who will be talking about this paper. So we're going to see how we can improve topic recommendation systems with these better semantic techniques. So please take it away.
Thank you. Hello, everyone. I'm Maddie, currently a PhD student at University of Waterloo. And I want to start this with a question. Does anybody know how many repositories GitHub hosts? 400 million repositories. And another example is a Stack Overflow with 23.5 million questions. Now you could imagine that if a developer wants to access a repository that uses Backbone.js and Django together, and looking through this huge corpora of data can quickly become a daunting task. So one solution that software information sites incorporate is tagging. For example, GitHub allows users to label their repositories with topics. Studies show that tags can improve the efficiency of tasks such as search, retrieval, navigation of entities. For example, if we go on GitHub and look for web development repositories, 160,000 results are listed. But if we select a programming language, a tag, like Python, the number of results goes down to 5,000. Studies also suggest that the completeness of the set of tags are important to improve the visibility of entities. If you select just 2 tags for a repository, you can just access them through those tags. But if you set a more complete set of tags, not only can you access them through the 2 originally assigned ones, you can access the repository through a lot more aspects of its identity. Tags have explicit informations, for example, back1.js, it's back1.js, and they also have implicit informations. For example, back1.js is a library. It is used in web development. It works with RESTful APIs, and it also is used for front-end functionalities. Knowledge graphs can model such implicit information, and it has been shown that knowledge graphs are very useful tools to improve the information retrieval and recommendation tasks, to the point that Google uses knowledge graphs as a layer in their search engine. So you could imagine that using a knowledge graph of software engineering and development topics can improve the efficiency of topic recommendation for entities. For that, we first construct a knowledge graph of software topics. We then use this knowledge graph in topic augmentation and topic recommendation tasks. To construct the knowledge graph, we take at the time, almost 400 GitHub featured topics, and we initialize a knowledge graph of such topics, and then we ask the community, the practitioners from the community, to first evaluate these relationships and also provide us with more knowledge in the form of more relationships. We then refine these new relationships and ask the practitioners to, again, evaluate and give us more information. This process happens iteratively until we curate a knowledge graph with more than 2,000 relationships of 13 different types among 863 topics. We then use this knowledge graph in the topic augmentation task. So to have a more complete set of topics assigned to a repository, we start by the topics that the user assigns to the repository, and we apply a spreading activation algorithm to identify more relevant topics to the ones that are already assigned. Using this technique, we outperform the baselines by 67% in average success rate, which accounts for the number of successful recommendations, and by 219% in mean average precision, which accounts for both the number of successful recommendations and the ranking of the recommendations in the recommendation list. We also use the same model and configure it with a text classifier to come up with a standalone topic recommendation system. To do that, we take 150,000 repositories labeled with 236 of the GitHub featured tasks and train a multi-class, multi-label text classifier over this data. Once the text classifier predicts a set of topics for the repository, we use these topics as the set of initial activated nodes on the knowledge graph, and again, apply a spreading activation to complete the set of recommendations. Using this method, we outperform the baselines by 136% in terms of average success rate and by 150% in terms of mean average precision. So to recap, we first constructed a knowledge graph of 863 community curated topics. We use them in the topic augmentation task and topic recommendation task, and we show that incorporating knowledge graphs can improve the efficiency of such tasks. Thank you for your attention. Please go ahead and give this paper a read, and if you need to discuss things, feel free to reach out to us.
You know, it's great to see just how much improved we can get using these, you know, trying to enhance things with the knowledge graph, with, you know, bringing in extra information, things like that. Mm-hmm. Have you considered, like, you know, approaching GitHub or, you know, like talking to communities to see if this is something that might actually, you know, be useful for them in the long run, or, you know, how would you see this actually being integrated, you know, into a like developer community-facing tool?
Actually, that was the original plan, and I believe that it can help a lot because the GitHub featured topics are also curated manually. And one critique that could be valid for this technique is that the knowledge graph is curated manually and through a large effort by the community. But I believe that's the case with any high-quality set of topics, and GitHub is curating the set of topics, but they're not looking into this semantic relationships. So yes, that could be actually very useful for such cases.
Algorithm for the prediction of the topics, is that graph-based or it's regular kind of supervised learning based?
For which components? We have two components. There's a text classifier for the topic recommendation that works based on supervised learning. And there's the knowledge graph-based recommender that works based on the spreading activation algorithm. So the set of topics that are fed to the knowledge graph are activated, and this activation score is spread across the edges of the knowledge graph to other nodes. And based on the popularity of the topics and the ranking of the number of use cases for that topics, we rank the activated nodes, and then based on the ranking, we select the top 3 or top 5 and recommend that.
Gotcha. Okay, thank you.
No worries.
Excellent. Let's thank Maddie one more time. Thank you very much. All right, so it looks like that will actually conclude our session for this afternoon. So thank you everybody for attending. I hope you're able to get something out of this to see all these really interesting advancements in recommender systems. Let's give all of our speakers one last round of applause.